Cool, well, thank you very much. So that's great to have heard from Ros and Andy there, because they've partially covered kind of some of the concepts that I'm going to talk about today. And I also want to comment that it's so great to have heard so much about oxygen. Most of what we hear in regards to the Earth system and I guess our current thinking is generally about CO2. And I think it is really important that we do remember that oxygen is the air that we breathe, so we do need to consider its regulation as well. So I'm going to talk about that today. So to follow on from the theme, this equation, or this rough equation, shows the most powerful biological process on our planet. And as you've already heard, but perhaps this wasn't shown, it's the rough equation for photosynthesis. And what it shows that amazingly, plants take carbon dioxide from the atmosphere, they combine it with water, and almost just drink in pure sunlight. And in doing so, they create their food, so carbohydrates, and in doing so, they release atmospheric oxygen, creating the habitable planet that we live on today. So this shows the last 500 million years of Earth history. So we've heard kind of more from Andy, this deeper time, oxygenation event, and similar from Ros, who also moved on to the future. But I'm showing here the last 500 million years of Earth history. So behind you on my left is the levels of carbon dioxide through Earth's history, and on the right, this is the abundance of oxygen. And rather than thinking about cyanobacteria or algae, I've marked the major points of evolution of forest ecosystems, so the evolution of and the spread of major forest ecosystems on our planet. And we can see that before the evolution of forested ecosystems, carbon dioxide levels were some 10 times higher than they are today, which led to global temperatures being around 10 degrees hotter than they are today. Whereas oxygen was at least half the amount that it is today. And we can see that as forests spread across the planet, we saw this dramatic fall in carbon dioxide levels and a coincident dramatic rise in atmospheric oxygen levels. And this is kind of like looking at photosynthesis on a giant scale. In other words, the evolution of plants, that is large terrestrial ecosystems have revolutionized our planet. So you might be wondering, well, if plants are producing all this oxygen, why doesn't oxygen just keep rising? Well, luckily, animals evolved on the planet as well. And of course, when we eat plants, particularly if you're vegetarian, like we are at this conference currently, you eat plant material, and in doing so, you release oxygen into you take in oxygen from the atmosphere, releasing carbon dioxide, water, to provide your energy. So it's a really nice balance. In other words, animals, like ourselves, reverse the jobs that the plants have done, at least on the short term. But you're probably wondering, hang on, think of all those forests out there, still out there today, despite all our efforts at deforestation. Why doesn't oxygen keep rising and rising? Well, luckily, as Ros mentioned, Luckily, as we bury carbon, we also continue to leak atmospheric oxygen. And in fact, each atom of carbon buried is the equivalent of 1 mole of oxygen release. And the reason this works in releasing oxygen over the long term is that if we think of large litter layers, we think of carbon being trapped in soils, we think of lots of carbon buried in peatlands, through to coal and geological stores of carbon. What that means is that over the long-term Earth history, these pieces of carbon are locked away so that animals can't consume that organic material, meaning that our levels of oxygen in the atmosphere stay high enough by creating this 1 mole of oxygen leak. Ooh. And despite this continued production of oxygen and the burial of organic remains, oxygen levels appear to have never strayed too far. So since this big increase in oxygen, there's been quite rapid swings, but somehow the Earth system has always regulated it within these bounds. And this seems really quite amazing because all the oxygen in the atmosphere and the oceans is entirely replaced every 3 million years. Yet over the last 300 million years, its abundance has actually varied less than a factor or 2. So as Ros mentioned, this is in part because processes remove oxygen from the atmosphere, stopping it getting out of control. And one of the easiest ways to visualize this is if you look at this US landscape, those rocks are red because they contain iron that's reacted with oxygen to make them red. Essentially, they've gone rusty. And when iron combines with water to form rust, it steals 3 oxygen molecules from the atmosphere. So once they've formed that rust in a rock and become trapped for millions of years, those oxygen molecules are no longer in the atmosphere. And this is just one example of binding of oxygen to elements and minerals. It happens with other minerals as well, as Ros outlined. But sometimes rusting can't always cope. So this is a coal mine, as you can see, and we've got some red rocks, but we've got a lot more black rocks. So essentially, sometimes plant burial happens in a much greater scale. So organic matter is buried on a much greater scale than there are rust and other minerals and rocks able to cope with drawing that oxygen out in the atmosphere. And so this means that there must also be another process on the planet that helps regulate the abundance of oxygen in our atmosphere. And in 1978, Andy Watson, who just spoke a minute ago, along with James Lovelock and Lynn Margulis, proposed that actually fires are responsible for, in part, regulating the abundance of oxygen in the atmosphere. And this is because fires need oxygen and air in order to burn. So you're probably all familiar with, perhaps if you were trying to start a fire, you'd either blow on it or you'd take some bellows to kind of force extra air at that fire to cause those flames to leap into life. So we all kind of do this naturally. So, well, what is the effect of oxygen on fires? So here's that work by Andy Watson, James Lovelock and Lynn Margulis, and they started looking at how increasing atmospheric oxygen increased the relative probability of ignition for different moisture contents of fuel. And we can see that as you increase oxygen, all his different fuel moistures generally had this similar shape where increasing oxygen meant that the fires were easier to ignite. More recently, Andy's finally decided to write up his PhD thesis. We have increasing atmospheric oxygen, increasing fuel moisture, and we can see that these two link to the relative rate of flame spread, where as you increase oxygen, the spread of flames increases, and this can also happen at higher fuel moistures. So wet fuel can even carry a fire compared to drier fuel. Some work from myself also was did some experiments where we then ran a model to look at if you increase atmospheric oxygen, does this increase the burned area? And hopefully you saw those tracking their way across, my little fires spreading across. And we can see that this is one for modern day atmospheric oxygen levels, and this is what we would predict for 24% atmospheric oxygen. So we can see that you would get much larger burned areas under high oxygen. And then more recently, we've also looked at damage to those ecosystems. So if you imagine a fire burning in the surface of a forest, it has certain height flames that can cause damage to the trees above. And this is the different moisture levels that we could suggest, and this is how high those flames can scorch into the forest canopy. And this line shows the results for modern day atmospheric oxygen levels, and this shows the results for if we assume 26% atmospheric oxygen. And we can see that we double the amount of damage that we can do to crowns. So essentially, if we increase oxygen, fire gets a lot worse. I could have just said it that simply, but I just wanted to show some of the research that's been done around this. So this is a picture from today. So imagine what this picture would look like if atmospheric oxygen levels were 10% higher than today. That's a pretty scary thought. So then how might this fire response then prevent oxygen continuing to rise? So I've put together a kind of very simplified cartoon to tell a short story about this. It totally ignores the ocean, but that comes later. This is the first part of the regulation of fire and oxygen. Okay, so trees grow, and as they do, they release oxygen into the atmosphere. Organisms breathe in the oxygen as they eat the plant material, but some plant material doesn't get consumed. This unconsumed plant material builds up, causing a slow leak of unconsumed oxygen to the atmosphere. Higher oxygen makes fires more easily ignitable. Trees and plants are killed, which are the source of the oxygen and the organic material. This reduces the number of plants and the amount of plant material that is available to be buried out of reach of consumption. So whilst oxygen is high, frequent and intense fires gradually erode forest, causing gradual loss of the amount of land covered by large terrestrial ecosystems. As forests diminish, less plant material is produced and less is hidden away from consumption, generally slowing the leaking oxygen tap. The oxygen leak slows and oxygen levels fall in the atmosphere, and fires become less frequent and forestry grow. So if we were to kind of plot this idea on a graph through time, we'd have something like this. So this is the last 400 million years of Earth history, and this is this sort of area burned idea, the probability that a certain amount of area will be burned. And based on this, we can see that there's been times in Earth history when there's been more fire, times when there's been less fire, and times again when there's been more fire, and here we are in our present day. And we can see that when there's more fire, our total terrestrial biomass should be suppressed because there's all these frequent fires and plants can't grow back as quickly. Whereas when there's less fire, our vegetation can expand. So basically, when there's less vegetation because of more fire, we're burying less carbon, we're releasing less oxygen, and then the opposite is true. As we have more biomass, we bury more carbon, and we get to release the oxygen. So we've basically got a nice balance. So then where would we be without fire? So this is a model of atmospheric oxygen through time by Tim. And what we've got is the last 350 million years of Earth history here, and the amount of oxygen on this scale. So this green line shows broadly the prediction of what the level of oxygen would be in the atmosphere if we didn't have this influence of fire on vegetation through time. And this red line is what we can predict by including this fire-based vegetation feedback. And we can see that today, if we include vegetation, we get quite a decent result. The oxygen is at the right level. Whereas if we don't include this fire feedback to ecosystems, it would predict that oxygen is around 24%, which is probably too high, and we would have a very flammable world, as the other results showed. So it's all about balance. It's all about these relationships. But the question now is, well, does this balance actually still exist? So we've entered what we could term the Piracy. So, of course, we spend our time putting out large fires because man has an inherent fear of fire, except for me, who really quite like starting them for research purposes, and those who are among us who perhaps enjoy a bit of arson, or maybe they did when they were a teenager, perhaps. Anyway, so due to man's activities, perhaps the natural balance of ecosystems and fire is now beyond its ability to regulate core processes, because our pyrogenic activities hugely blur the natural balance. Have we taken away Gaia's fire? So I wanted to bring you this story because we are a community that cares about our planet, our forests and ecosystems, and finding the best ways to manage our planet, and indeed the best ways to manage fire for nature, but also for man's safety, because I think that's one of the challenges that we've had, this balance between safety and managing for nature, because as you can see, fires have been part of the Earth system for 420 million years, in fact. So us cutting them out maybe isn't such a good idea. And my suggestion is that the challenges for wildland fire management need to consider a new kind of resilience. It's very rare for people working on fire to ever consider long-term resilience. And this is perhaps even longer-term resilience than we might need to think about in regards to CO2. Because our management of wildfires and ecosystems has to incorporate into its vision that natural balances are themselves a resource. that critically secure the balance of long-term Earth system processes over millions of years, and indeed the air that we breathe. Thank you.
Thank you. Is there something analogous to wildlife or wildfires that occurs in the oceans?
Well, actually, what I haven't said there, and maybe this does or doesn't answer your question, but the wildfires on the land and their effect on vegetation influences phosphorus redistribution across the Earth's surface and into the ocean. So phosphorus is one of the limiting nutrients in the ocean. And so if we change that flux of phosphorus by decreasing land vegetation by this interaction of fires, it actually changes the phosphorus flux to the ocean. And therefore, we actually change ocean productivity as well. And this can be via two ways. You can ask Lee Kump about his version, and you can ask Tim about his version, because they have complementary but slightly different mechanisms that both involve carbon burial and phosphorus. But I just missed this whole part out because then I'd have to have an hour-long talk.
Lee, one more question.
Quick question, Lee Klinger. I've been working on fire ecology in California, and what we're finding there is that when you have frequent fires, you don't get fuel buildup. So the trees actually survive. In fact, the trees love ground fires. It's the canopy fires that are destructive. So if you have higher oxygen, maybe you're going to have higher ignition, faster ignition rates, more frequent ignition rates before the fuels build up, and you're going to have healthy ground fires, which are going to preserve the trees. Just a thought. What do you think of that?
Yeah, it's a possibility, but I mean, we end up with flame lengths that are double the height from those surface fires. So I guess we'd have to get a lot more branch shedding conifers evolving in order to make sure that prevented those crown fires. So we kind of got to think about fire behaviour in all aspects, I think. So not just ignitions and frequency, because that's what a lot of the literature has talked about, but actually it's the behaviour of those fires as well. They would be so much more intense, so much more rapidly spreading. But so we need to think of that as a whole. Thanks.
Great. Let's thank Claire again. That was fantastic.
Thank you.
Give it to Seb.